Hello and welcome to Geometry Vocabulary and Vocabulary Practice with the Essentials of Geometry. In this video, we will analyze figures to identify points, lines, and planes, and identify intersections of lines and planes. That means we will also be drawing and modeling points, lines, planes, line segments, rays, and angles, and naming and identifying points, lines, planes, the intersections using words and symbols, classifying lines as parallel, perpendicular, intersecting, and skew, classifying planes as parallel, perpendicular, or intersecting, classifying points as collinear and or coplanar, and then also determining what geometric term models a real-world object. Here are some of the standards that we are going to be hitting today. These are from the Florida's Best Standards for Mathematics. So let's go ahead and get started with points, lines, and planes. So we've seen points, lines, and planes in pre-algebra and Algebra 1. However, we've also been working with these things even throughout elementary and middle school math. In geometry, you're going to hear a lot of the terms where we think we know what they are, but in geometry, they're going to become a lot more specific and a lot more defined. So let's go ahead and start with points, lines, and planes. These are actually considered undefined terms. And the reason why they don't quite have a definition is really because they can only be explained using descriptions and examples. When it comes to a point is literally just a location in space, and space is defined as the set of all points. And so even if we thought about, let's say, outer space, if we thought about a planet would just be a point in outer space. That means that space is also infinite, and it has an infinite number of points. In geometry, a lot of what we do depends on a couple of definitions. So 2 points are always going to define a line. So as long as you have 2 points, we are able to connect them with a line. So that doesn't mean that there's only 2 points on a line. That just means once we have 2 points, we can make a line between them. There's an infinite number of points on a line. There's an infinite number of points between A and B, and then we also see that our line extends forever in both directions. 3 non-collinear points always define a plane. So the word collinear means on the same line. So if we are looking at line AB here, A and B are 2 collinear points. They can be on the same line here. However, if we're talking about 3 non-collinear points, we're talking about 3 points that are not on the same line. So I could draw a line between A and B. I could draw a line between B and C. I could even draw a line between A and C. However, there is no straight line that connects all 3 of these. So if you have 3 non-collinear points, they can lay on exactly 1 flat surface. When it comes to 2 points, there's only 1 line that could be drawn between them. And we'll see a little bit more of this coming up soon. So let's go ahead and look at some of these vocabulary words. So we know that a point is drawn with a dot, and then we name it using a capital letter. So if I were to name what this model is right here, I would name this point A. Some important things about a point is just a location. It doesn't have a size or a shape. If I were to identify 6 here on my number line, even if I made this dot a little bit bigger, it really doesn't change my location. Even if I made this a little bit more square, it still wouldn't change my location. So a point doesn't really have a size or a shape. That means it has 0 dimensions. It doesn't have length, it doesn't have width, and it doesn't have height. There's nothing about this point that I'm making here on a 6 that I would measure with a ruler. Okay, and then the same thing with a coordinate plane. We've worked with planes, points before on number lines and planes, where it's just giving me a location. When it comes to a line, we know that it's going to be a straight line with arrows on the end, demonstrating that it goes on forever in both directions. It has 1 dimension. The only thing that I could measure about a line is its length, so it only has 1 dimension. If we were to name this line, we would name it using 2 capital letters, and those would be points on the line. So A and B are points on the line, and I could call this line AB. I could also, instead of writing out the word line, I could put AB and then put the double-sided arrow symbol on the top, and that is read as line AB. You can't forget to put those arrows on there. Also, there are times where we can name a line with a lowercase letter, like this. That doesn't mean that M is a point on the line. It's simply just a name of the line. So we could also call this line M, and in some textbooks and worksheets you may also see it as M with that double arrowed symbol on the top. And this is kind of similar to something we saw in Algebra 1, where you may see a line and they name it something like f of x, and then you had another line and they called it g of x, and that's just using a name for the line to kind of distinguish it from one to another so you know which one you're talking about. So we won't see this as much in geometry. This was them using their function names. However, in geometry you may see where they are calling one of these line M and then maybe line P or something to that effect. So we briefly mentioned planes, and the one plane that all of us have seen before is the coordinate plane. So a plane is named by 3 non-collinear points. So let's say we have D, E, and F here. Notice that I can't connect all of these with a straight line. That means that those are 3 non-collinear points. So these are points not on the same line. And to model a generic plane, we use a 4-sided slanted figure, so we're going to use a parallelogram here. However, a plane just means a flat surface. So when we start getting into 3D images, say a pyramid, that flat surface is no longer going to be shown as a parallelogram. It could be a triangle, it could be a square, it could be a rectangle shaped flat surface. So you're not always going to see it quite like this. So this is just to model a generic plane, and we would name this plane DEF. And there's no certain order that you have to have these non-collinear points in, so we could also call this plane EFD, and so forth. And so if you're not naming your plane exactly like somebody else, that's totally okay. So there's 6 different combinations that we could have for this one. And just like with lines having an alternative name, you'll also see this for these as well. So we could call this plane Q. And notice that Q is in the corner and it doesn't have a dot next to it. That means that Q is not a point on the plane, it's simply just a name. So we could also call this plane Q. And when you're naming a plane, you cannot use a combination of the name Q with the non-collinear points. So it needs to be named either one or the other. So I'm either using a combination of 3 points that are not all on the same line that lay on the plane. So a combination of D, E, and F. Or I'm using Q. So I wouldn't be able to say something like QED as a name of the plane. And a plane goes on forever in all directions. So you could kind of think about a plane as being a flat surface. So if you're thinking about the floor being a flat surface, and then a real plane goes on forever. So imagining that that floor is extending forever. And one of the most common planes that we know about is the coordinate plane. But even if we drew, let's say, a rectangle here on this plane, we can see that it has 2 different dimensions. So we have length and width. You may also hear this as base and height. But either way, we know that a flat surface only has 2 dimensions. That's why when we're talking about area, we're talking about units squared or square units because it only has 2 dimensions. And now let's go ahead and jump into line segments. So line segments are still one-dimensional. They only have length, but they do not go on forever. They have 2 specific endpoints. So we could have something like P and Q here. And if I was to name this, it would be line segment PQ. And when we are naming lines and line segments, there isn't something that goes first. There's nothing to say that P has to go first here. But when we go to name it with a symbol, you're just going to put a line over it. You're not going to put that double-sided arrow. So for this one, we could put PQ or we could put QP. And so when we're naming line segments, you're only going to be using the 2 endpoints. Even if you have multiple points, we know that there's an infinite number of points between P and Q. Even if this had another point in between, if we're talking about this entire segment here, we're just going to name it PQ or QP. You're not going to call it PWQ or anything like that. So just kind of keep that in mind as you guys are looking at line segments. Going back to the line that we drew earlier, notice the difference between lines and line segments. Lines have those arrows at the end, and then remember that we could also name it going the other direction as well. But lines are going to continue extending on forever, where those line segments are not. And we've been working with line segments for a very long time. You may have used rulers and tape measures in your math classes before, and that leads you into the ruler postulate. And all that means is if I were to draw a line segment, let's say going from 4 to 14. It just states that every point on a number line or a segment can coordinate with a real number, and the length or the distance is the absolute value of the difference between those 2 points. So the distance is going to be, if this was x1 and x2, it's going to be the absolute value of x2 minus x1. And so 14 minus 4 is going to give us 10, and the absolute value of 10 is just 10. And so I know that there are 10 centimeters or 10 units in between these two numbers. So the ruler postulate just says that we can assign those points to real numbers and calculate the distance. And now, kind of journeying back into middle school math, we also have rays. Rays are basically half a line, where we took a line and we cut it somewhere. And for this ray, let's say we have H and I. And so if I were to name this, it has to be with the endpoint in front, and we're going to use those 2 points that are on that ray. So it's going to be ray HI, and H has to be in the front. So we can also name it with that symbol on the top, with the endpoint kind of going here and then extending through I. So it kind of tells us where it's starting. Now H has to be in the front when you name a ray. It has to begin with that endpoint. You would not be able to call it something like IH, even if you put the arrow going this way. That's not allowed. It has to be with that endpoint first. And rays are also one-dimensional. They only have length, and it's half of infinity, which is still infinity, so it still goes on forever. So the length of a ray is also infinite. Although we're not covering angles as much in this particular part of geometry, we're going to go ahead and recap on how we name them and draw them. So let's say we have this angle right here, and we're going to label this A, B, and C. So it's drawn using 2 rays. So I can see there's a ray here and a ray here that share an endpoint, and that shared endpoint is called the vertex. So in this case, B is going to be our vertex. And there's a couple of different ways we can name an angle. So this can be angle ABC. Notice that the vertex is going to be in the middle. And when you are naming, you kind of want to go in order, and you kind of want to trace it with your finger. So A, B, C, and that tells us that we're talking about this angle here in the middle. Or we could go the opposite direction. We can say C, B, and then A. That's also talking about that center point there. So instead of saying angle, I'm going to use the angle symbol. And so we could also call this CBA. And notice that B is still in the center. When you have an angle that is by itself, and there's only one angle that you're looking at, you can also name it by the vertex like that. However, once you have a vertex that's being shared among multiple angles, so say we have something like ABC, but now it's part of this straight angle here. I'm going to add D on this side. I can't call this angle B anymore because I don't know if you're talking about this obtuse angle here, which is DBA or ABD. I can't tell if you're talking about this acute angle, ABC or CBA, talking about this angle here on the side, or if you're talking about this straight angle, which is DBC or CBD. So when it comes to angles, you can only call them by just the vertex if it's just a singular angle there. Also, you may also see it labeled with a number without the degree measure. And so we could also call this angle 4. In geometry, you're going to see where they often name angles using numbers. So like this obtuse angle may be called angle 1, and then this one could be called angle 2. And then the straight angle would be a combination of angle 1 and angle 2, which we'll get into in the next unit. So there's multiple names that you could call it by. Just make sure you're kind of tracing it with your finger to make sure that you are naming it correctly. And the protractor postulate is very similar to the ruler postulate, and it's just talking about being able to attribute those rays to be going through to a certain number on a protractor, and that we would be able to measure that angle somewhere between 0 and 180 degrees. So now that we have covered our bases with our vocabulary, we've practiced with naming and how to kind of use our symbols to talk about these different geometric terms. Now let's go ahead and start getting into the relationships between them. So we know what parallel lines look like. We've seen those before. And so we know that they look something like this. And we know that parallel lines never touch or intersect, and they are also on the same plane. So thinking about parallel lines, there is a flat surface that can connect those two lines there. So when we think about the two parallel sides of our desk, we know that that flat surface of the tabletop is going to connect them. They also have the same slope or m value. So when we're thinking about slope-intercept form, which is y equals mx plus b, they're going to have the same m. When you are thinking about y minus y1 equals m times x minus x1, which is point slope form, they're going to have that same m value. And in Algebra 1, we just kind of stamped that they have no solution or no points in common, which says that they're never going to intersect or touch. So we know that there's an infinite number of points on this line, there's an infinite number of points on this line, but because they have the same slope, they're never actually going to run into each other. They're not going to have any points in common. When it comes to perpendicular lines, we can think about the x and the y axis of a coordinate plane. We know that those intersect at a 90-degree angle, so we put that little box there. And these are also going to be on the same plane as well. And these have negative reciprocal slopes. And we'll get into that later in geometry, but that just means that we are going to flip the fraction and then change the sign of the slope. And that's how we're going to know that they are perpendicular. And we're not always going to see just lines. We may also see something like a line segment, and then maybe a ray going like this, hitting at 90 degrees as well. So it's not always just lines. For intersecting lines, it's Perpendicular is just a type of intersecting lines. These are also going to be on the same plane. When we think about these, we have that flat surface that those lines can kind of sit on. And with intersecting lines, it just means that they hit each other, but not necessarily at 90 degrees. So it could look something like that. If we're looking at equations, they have different slopes. They're just not going to be, well, they could be negative reciprocal slopes. But as long as they have different slopes, we know that they're going to be intersecting somehow. Now, skew is the one where it's going to look a little bit different. So here I'm going to draw a cube. And I'm going to draw that by drawing two squares that are kind of the same size overlapping. And then I'm just going to connect the sides like that. And skew is a little bit weird and different. Here, if I were looking at these two lines here, I can see that they are going in the same direction. I can see that they're never going to touch each other. And so those are going to be parallel. Even if I was looking at even this one and this one, I can see that I could cut this cube in half diagonally and there would be a flat surface that could contain these two lines. So that's parallel. Then we have ones that look like these, and we can see that those are not only intersecting, but those are going to be perpendicular. Because we know that a cube has those nice 90-degree angles. Even if I was looking at these two though, even though it doesn't look like 90 degrees at face value, thinking about what this shape would look like in real life, knowing that this is a 3D figure, I know that this is still going to be 90 degrees, even though at face value that doesn't look like a 90-degree angle. Now, the one that's kind of strange is if I were to look at this line here and this line here. Even if they went on forever, they would never hit each other. However, they're not parallel either. And this is called skew. And notice that these two lines can touch the same plane. So this vertical line here is actually laying and part of this side plane here on the side of my cube. However, the line going across the top here is only intersecting or touching the corner of that plane and kind of driving through it. So this is called skew. When you have these two lines here, they never intersect, they never touch, they can kind of touch the same plane, but they're not in the same plane or laying on the same plane, but they're not parallel. Just like with lines, we can also classify planes as parallel, perpendicular, and intersecting. And we can draw these kind of, we're going to use those parallelograms again for these generic planes. So we can kind of think of this as a piece of paper. And then if I were to draw another piece of paper underneath it like that, we could also think about it in terms of our cube that we had. And if I was talking about parallel planes, I could think about this bottom of the cube and then this as being the top of my cube. And we see how it kind of looks like the picture that I just drew here. And then we've got perpendicular planes. And if you wanted to take a stab at drawing these, we could draw a vertical plane kind of like this. Then we could draw a horizontal plane like that, connect diagonally on the square here, and then we could erase or dot kind of dash those lines there. I'm just going to go ahead and completely erase them. And then we have something that looks like this, and we can kind of see this plane or flat figure here, and I'm going to make one color, and then we can kind of see this white one kind of going through it like this. We could also demonstrate this in our cube here, where we have the side and the bottom of our cube like this. And then we could add those little 90-degree boxes to show that they hit at a 90-degree angle. And then intersecting planes, they just mean that they cross but not necessarily at 90 degrees. And so they might look something a little bit more like this, where we can tell that it's not quite hitting at 90 degrees there. So now let's go ahead and talk about intersections. So we've kind of seen these already in Algebra 1. We know that the intersection of two lines is going to be a point. In Algebra 1, we were finding the intersection of two lines, and we were calling that the solution, right, of a system of linear equations. And so we know that the intersection of two lines is going to be that shared point that they have there. When it comes to planes, when you're thinking about two flat surfaces, it's going to be that line where they kind of meet in the middle. So thinking back to our cube that we had, and when we draw out our cube, the intersection of two planes, if I was talking about maybe the side and then the top, we can see that they meet here at this little edge here. And so the intersection of two planes is going to be a line. So if I were to kind of say this as a full sentence, I would say the intersection between plane Q, which is this horizontal one here, and plane P is line M. And so that's how I would say that fully. And now kind of stamping what we talked about in that very first slide when we first got started, talking about collinear and coplanar. So we know that there's an infinite number of points on a line. However, once we have 2 points, there's only one line that can connect them. And points that are on the same line are called collinear. So if I look at this line here, I can see that E, F, C, and G are all collinear points. They're all laying on that same line. I could also say that about A, B, C, and D are all collinear points. And then I also have this line here going through B and F. And so I could say that B and F are also collinear. However, if I were to ask you about A and E and ask you if they were collinear, even though we don't see the line there, I know that I could connect those 2 points with a line. So anytime someone is asking you about just 2 points, they're always going to be collinear, because I know that I could connect those two with a line. And so this is where it starts to get a little tricky in geometry. Even if it's not in the diagram, even if it's not drawn, you still have to know what the concept of collinear and coplanar is. So collinear means on the same line. So co means same or with, if you're an English whiz, and then we see this word line in linear, so same line. And then coplanar is very, very similar. co, same or with, and then we have plane kind of in here in this word here. So coplanar means on the same plane. When we're looking at this particular diagram, we kind of have this white plane being intersected by this gray plane here. So if I were to ask you about what points are coplanar, if I'm looking at this white plane, I could say M, A, B, and N are all on this white plane. If I'm looking at the gray plane, I could say P, A, B, and Q are all on the same plane. And notice where those two planes are meeting is right here. So that would be the intersection of those two planes. So the intersection of the white plane and the gray plane is going to be line AB. So the intersection is going to be AB. And then remember, planes go on forever. So even though it looks like those planes are stopping, this would actually continue on forever. So the intersection between those two would be line AB. And if I were to ask you about, let's say, M, A, and P, and if I were to ask you if those are coplanar, my answer would be yes, because three non-collinear points are always going to define a plane. So even though I wasn't drawing it, as long as these 3 points are not all in a row, there is a flat surface, a singular flat surface or plane that can connect them. I could take some type of sheet of paper and I could connect M, A, and P through those 3 points. So even though we don't see it in the diagram, M, A, and P are coplanar. If I name 2 points, they're always going to be collinear. If I name 3 non-collinear points, it's always going to be coplanar. So this is the part of the video where we are going to do some vocabulary practice. We have already covered all of the vocabulary, how to name and identify, but this is where we're going to actually start applying those. And so let's go ahead and start with some practice. So write the following in words. So we see PQ here, and it has that double-sided arrow on the top. And so this is going to be line PQ. And then remember, we could also name this as line QP. It's going to be the same no matter what. On the second one, we have that one-sided arrow, and so that's going to be ray UV. And remember, with rays, we wouldn't be able to change the order. The endpoint always has to go first. So we would not be able to call this ray VU. This third one here, we see that there is no arrows on either end, and so this is going to be line segment HG, or you could say line segment GH. Now, for explain the difference between ray CD and ray DC, first you need to be able to recognize that these are rays based on these symbols up top. But if you wanted to, you could draw this to explain the difference. On ray CD, we see that C is the endpoint. And then for ray DC, we can see that D is that endpoint there. So these two have different endpoints. Write the geometric term modeled by the following real-world objects. So a solar panel is very flat. We see it on roofs, and so those are going to be modeling a plane. For a pencil, we could either call this a line or a line segment. Typically on an assessment, they wouldn't give you both of these as an option. It's going to be one or the other. We don't have any real world objects that go on forever like an actual line would. So when we're talking about modeling, just like when we talked about the cube, we only see that one edge. But if we're talking about real planes, and those real kind of edges, like where they're meeting, we know that those would actually go on forever. So a pencil would be considered a line or a line segment. Light from a flashlight, it is starting at a source and then it's going on forever until it hits something. And so that is going to be a ray. And we hear that all the time, right? A ray of light, or UV rays or UVB rays, talking about the sun. A planet in the universe, we already talked about that being a point, a location in space. Tabletop is a flat surface, and so that's going to be a plane. A pencil eraser on a desk, I'm thinking about the eraser that you can, kind of take off of your pencil. And if it was just laying on the desk, that's just going to be a point. A telephone pole is going to be a line or line segment here, would be fine. And then where the wall meets the ceiling, so that kind of goes back to our cube, right? Where we had that wall, and then we're talking about where it's meeting the ceiling. And so all along that little line there is going to be where those two planes are going to meet. So the intersection of two planes is going to be a line. For this one, we're going to do a little bit of true and false. So it says number 1, points A, B, and C are collinear. There's no straight line that connects these, and so that is going to be false. These are not collinear, however, they are coplanar. They're all laying on this flat surface here. For number 2, it says points B, C, and D are coplanar. B, C, and D. Now, it does not lay on this plane that they give us. However, these three are three non-collinear points. And so even though we don't see the plane being drawn in the diagram, that's going to be true. For number 3, it says point C lies on line AB, and when I'm looking at line AB, which is this line right here, it does not go through C, and so that's going to be false. And it says for number 4, line AB lies on plane ABC. So that's just saying, does it lay on that plane? And in that case, it's going to be true. We can see that the plane is here, and that line is laying right on that flat surface. And if points A and B are creating that line and it's in ABC, that means that that line created by those 2 points are automatically going to be on the plane. And so that's going to be true. Then we've got line DE lies on plane ABC. And so DE is this line right here. Now, this one is not laying on the plane like we would kind of imagine a pencil laying on a sheet of paper. It's going through. And so it doesn't lay on the plane, but it does intersect the plane at point B. And you can see here where it has these dotted lines here, that just means that that part we can't actually see. So if I was sticking a pencil through a sheet of paper, there's part of the pencil I wouldn't see because that piece of paper is there, and then I would be able to see that pencil kind of showing at the bottom. So this part right here is the part of the pencil that I can't see. So anytime you see that dotted area, that's the line or the plane that's not showing because it's behind. And number 6 says points A, B, and C are coplanar. And that's going to be a yes, even if I didn't have that plane there. These are 3 non-collinear points, so that's automatically going to be true. and then points B and C are collinear. Even though I don't see the line between them, anytime they ask me about 2 points, I know that I would be able to connect them with a line. So this is going to automatically be true. For this one, it says circle correct names of plane K. So notice that K is not a point on the plane. There's no dot next to it. So this is just the name of the plane. And that's something we covered when we talked about how to name planes. And so we have plane K here, and we know that we can also name a plane by 3 non-collinear points that are on the plane. So I've got A on the plane, B on the plane, and C on the plane. So any combination of those 3 would be acceptable. So all of these would work. Now, when it comes to plane A, we can't just name a plane by one of its points. If I'm thinking about plane A, there's an infinite number of planes that could go through this. So kind of think about, if this was a singular point in space, how many sheets of paper could I have hitting through that point? There's an infinite number. It can hit at every single angle. The same thing with plane BC. If we are talking about a line going through BC, I could also have a plane kind of going at this angle, right? And hitting BC at different angles as well. So that doesn't work, because there's an infinite number of planes going through BC as well. So this one doesn't work either. And then it's asking us about plane ABD. While these have a plane that connect all of them, it is not the same as plane K. Point D is not on the plane, and so we wouldn't be able to use that one. And plane R, first of all, we can't name a plane with a lowercase letter like that. And R is the name of the line. We talked about how lines can be named with lowercase letters. And in this case, this is talking about line AB or BA, and it has another name, which is line R. And so we could not use that to name plane K. All right, now let's take a look at this diagram. Number 1 says, are points E and F collinear? I don't even have to look at the diagram to say that this is a yes or true. Even though it's not on there, as long as I'm talking about 2 points, I know that I would be able to connect them with a line, and so they are automatically going to be collinear no matter what. Name the intersection of plane R. So plane R is this vertical plane here, and then we've got plane Q going kind of through it. And they are meeting here at this line, and this is called line M, so we could say line M, or we could put M with that double arrow would be fine. Name 2 lines that contain point E. So we want to name any line that goes through E, and so we could name line DE. We could have also called that line ED. And then also notice that we have that that lowercase letter on the end here, and so we could call that line P. However, all of those are the same line, and it's asking us for 2 lines that contain point E. And from number 2, we know that there's also a line that exists between E and F. So we could have also said line EF, or FE would have been acceptable, and that would have been our 2 different lines. Number 4 says name the plane that contains point F. So when they have points here like this, they're not going to have it as if F is behind plane Q. Notice that this part of the plane For Q, we can't see because we have this dotted piece here. And so when we're thinking about like what is visible, when it comes to Q, this is the part that we can see of plane Q. We see it here, and then it's being cut off at M, and then we can see the part that's behind it like that. And so if that's the case, F is laying on plane Q. And so it kind of takes a little bit to kind of get used to how to kind of look at these 3D figures. But Q is the one that we can see here. And then out of plane R is this vertical plane. And so for plane R, we can see this whole thing here. Notice that that back dotted piece of Q we can't see. And then here we can see R. And so F is clearly on plane Q. And then notice for plane R, this is the part that you can't see of R because Q is kind of covering it up. So it takes a while to kind of get used to reading these and looking at these, but F is going to be on plane Q. And then number 5 says, give another name for DE, and that's something we already did in number 3, so we could also say ED, or we could have said plane P. So line ED or plane P would have been fine for that one. For this question, it says draw and label a figure to represent the relationship. So we're just going to take this piece by piece. First of all, they give us these 4 points, A, B, C, and D. So let's go ahead and get those onto our coordinate plane. Make sure that you take notice that our axes are going by 2. When you went to put B on your coordinate plane, you should have noticed that that would have been off the coordinate plane if they were actually going by 1. So we took care of the points, and then they also tell us that we have line AB and line CD. So let's go ahead and connect those points. And take notice that when we added our lines, that they have our arrows on them to make sure that they're actual lines. When we were in Algebra 1, sometimes we were lazy about making sure that we put those arrows on the end. In geometry, you have to make sure that you have those, okay? All right, so it also says that our lines are intersecting at point P. And so where they are intersecting, I'm going to label that as P. And then it says point E is coplanar with these points, which means that it's somewhere on this coordinate plane, right? But not collinear with AB and CD. So I can't put point E on one of those lines or else it would be collinear. So that just means that E can be anywhere on this plane but not on those lines. So I could put E here, I could put E up here, I could put E here. So E can go anywhere on this coordinate plane but not on those lines. So anywhere would have been fine. All right, now let's take a look at this one. It says how many planes appear in the picture, and then we're going to name them. So we see this 3D figure is kind of laying on this flat surface, which is plane P. So that's going to be one of our planes, is going to be plane P. And we could also name plane P by any of the any 3 non-collinear points on that plane. So we could name it H, I, and then D. Or we could have named it I, G, D. As long as there are 3 points that are on this flat surface that are not all in a row. So any of those would have been fine. as long as they're not all in a row. So I wouldn't be able to call it something like HIC or ICF because those points are all in a row. Now, when you're thinking about how many of these planes there are, we've got this flat surface, which is P, and then we also have the base of our pyramid here, our pentagonal pyramid. When you have a 3D shape laying on a flat surface like this base becomes part of the plane that it actually lays on. So that does not count as a separate plane. This is part of plane P. All right, and now let's go ahead and start naming some of the others. So I'm going to start with this side of our pyramid, and we can't call it A, B, C because those are collinear. So I have to use point D at some point. So I could say plane ACD, I could say ABD or CBD, but I have to use point D at some point because I can't use a combination of A, B, and C alone. Okay, and then now let's go to this back side here. Same thing with this one. I wouldn't be able to call it any combination of A, B, and C. I would have to use G somewhere. So I've got plane GAC would be totally fine. BCG would be fine. CAG would be fine. Okay, now let's go to this back panel here on our pyramid. We can say plane AGF, and any combination of those three would be fine. Then coming around to the front and looking at that front right side, we have plane AEF, and then this very front panel here, this front panel here, we have ADE. And any combination or order with those three would be totally fine. And then remember that this bottom side here is part of plane P. So that means we only have 6 planes appearing in this particular figure. Number 2 says name 4 points that are collinear. We can see here that the only 4 collinear points here are laying on this line here, and so that's going to be H, I, C, and F. For number 3, it says name the intersection of plane GAC. So GAC is going to be this panel. And then we're seeing where it connects to plane P. Well, this whole edge of that flat side of that pyramid is hitting the tabletop or plane P. And so that is going to be line CG. And remember, when we're thinking about planes and these lines, they're continuing on forever. Notice that on our pyramid, our planes are flat surfaces, and on a pyramid, we see that these flat surfaces are triangles instead of parallelograms. All right, now looking at number 4. Number 4 says, where does line JI and CD intersect? So you want to imagine if these lines were going on forever. Even though it looks as if I did this at face value and just continued this line on forever, you could possibly say, oh, well, it hits at point J. No, it doesn't. If we're thinking about this as a pencil going through a desk, right? And then this side here, if this continued on forever, it would be behind. It's never going to hit that pencil that's going through my desk at this point. And so this would be they do not intersect. We can also see that they're not going in the same direction, so they're not parallel. These are going to be skew. Okay, so they don't intersect. These lines would be example of skew lines. And our last one here, we have a biplane here, and it says each wing models a what? When we're thinking about a biplane and what it actually looks like, these wings are flat surfaces. And so there's a pair of parallel flat surfaces here, and so each wing models a plane. They're flat. The intersection of a strut and a wing, so the struts are these poles here that are connecting those parallel planes. And so where a line meets a plane is kind of like that pencil that goes through the plane, right? Something like this, and then it comes out through the bottom. And so that is going to be a point. So the intersection of a plane and a line is going to be a point. And then the crossing of two flying wires, we see that our flying wires are kind of like lines here. And so the point where they would intersect, okay, is going to be a point. And that concludes our video on our geometric terms, how we name, how we can identify, and then we also just completed some practice. So make sure that you are going through and studying your vocab, especially for this first test and for your EOC. Thanks, and I'll see you in the next video.